Today we're going to start our conversation about the central nervous system. And we're going to start with like general discussion. What are the parts that we're going to talk about in each unit, okay? Cells of the central nervous system. We're basically going to divide even each chapter into smaller bits. So it will be structured, each chapter will be structured in like 3-4 little subunits, logical subunits. So let's talk about CNS. Let's talk about nervous system. And let's talk about its anatomy, sort of functional anatomy. So nervous system can be divided into central, CNS, right? And peripheral, PNS. So what is the function of the central nervous system? Functionally, it is basically a processing of information. Peripheral nervous system is we're going to put it as transmission of information. Okay. So what are the parts of which system? The central nervous system, there are 3 parts. Brain, brainstem, and spinal cord. So what is the function of each of those? The brain, we can simply put conscious activities. Okay, things like, it is a bit more than that, but if you think about the function of the brain, you consider conscious movements, conscious understanding of sensation, thinking, memory, conscious control over emotions themselves. All of it is in the brain. We good so far? Now, what is the function of a brainstem? I'm going to put here visceral controls. So things like control of the blood pressure, control of the respiration rate, reflexes such as urination or defecation or hiccuping or whatever. You know, everything that you're not really controlling consciously. Does that make sense? We good? Now, you have to understand that these parts of the nervous system do not exist separately from each other. For example, when you are scared, the sense that you are scared, you know that the situation is dangerous, right? That understanding comes from the brain. Your brain perceives the situation as dangerous. Now, your response to it, elevated heart rate, dilated pupils, increased respiration, increased perspiration, that's the response to the brainstem. You see? So your conscious perception is accompanied by some visceral responses, and that's the brainstem. And then you have spinal cord. So we can put here that it is a transmission route because it allows signals to go to the brainstem and the brain up, and from brainstem and the brain down. Does that make sense? And also it is responsible for a whole bunch of reflexes. So automatic response. Okay, so now what's the function? What's the function of a PNS, peripheral nervous system? Well, parts and function. So first of all, it's receptors. and nerves. Receptors receive the outside stimuli. Okay, so for instance, what's the temperature? At 70. You feel that it's a little bit chilly because of your thermoreceptors. Okay, you hear me because of the mechanoreceptors in your ears. Okay, you see me because of the photoreceptors in your eyes. Does that make sense? And then nerves transmit the information. Does that make sense? This functional anatomy of the of the nervous system. Does it make sense? Now, brain, brainstem, spinal cord. I don't mention. That's kind of good. Okay? We good so far? Now I want to add some more terminology. We will come back over and over to that terminology, but I want you to be aware of the informational flow in the nervous system in general. So it all starts with the, change the color just for the sake of it. It all starts with the stimulus. Okay? Now stimulus is sensed by the receptor. Signal, sensory signal, goes through the sensory nerve. Okay? Sensory nerve gets the signal to the central nervous system. And it doesn't matter. It can be brainstem, it can be spinal cord, or it can be brain. Now, the function of CNS in general is processing of information, right? So, central nervous system processes that information, generates the response, which goes to the motor nerve, okay? And motor nerve delivers the response to the effect. Does that make sense? This line of events here. Now, an example would be, I tell you to write something down. I tell you, write down the word brain. That's stimulus. Receptor is in your ears. Does that make sense? The signal goes from that receptor through the vestibulocochlear nerve, sensory nerve, to your brain. Your brain processes it, realizes, okay, this dude told us to write something down. So brain generates a special pattern of signals that go through the motor nerve, that would be a mix of signals going through the median, ulnar, and radial nerves to your fingers. And your skeletal muscles serve as a vector when you write things down. Does that make sense? Do you understand what I just explained? You can break down any human action that is triggered by the external stimuli in this manner. Whether you're pulling your hand away from the hot plate, whether you're writing something down, whether you have an urge to pee. The responses can be conscious, they can be automatic responses that you can't control, but it's always one way. Does that make sense? Always, that's important. The signal travels always one way. So, for instance, and you see how many times I say this, it is important. Sensory signal will always go from the periphery of the body, skin or organ, whatever, to the CNS. Motor signal will always go from the CNS to the periphery. Understood? Now, the word periphery here does not mean that it should be very far, like the toes. Periphery means not in the central nervous system. You understand? So, for instance, these muscles in your neck, they're pretty close to your spinal cord. This is the periphery. They're not the part of science. Am I clear here? We good? Okay, a couple more things about functional classification of the nervous system. Now, we can divide nervous system by the function into a motor and sensory. Does it make sense? It can be applied better to the peripheral nervous system because you have a motor branch and a sensory branch. And motor can be divided into somatic and autonomic. Okay? Now we're going to do some classification for sensory as well. It's not as rock solid. It's going to be somatic. Special senses. Now, let's figure out which meaning we put into each of these words when we talk about. When we talk about somatic motor, that's your skeletal muscles as effectors, okay? That's your conscious responses. You writing, me talking, you like adjusting your masks, turning left and right in your chairs, bending. I'm not making fun because you provide me with examples. Stretching, okay? All of it are somatic responses. You control this. Does that make sense? Autonomic responses, everything. How your heart beats, how you produce saliva, you cry, you cough. All of this are autonomic responses. Does that make sense? We're going to use these terms. And the effectors for autonomic responses will be cardiac muscle, smooth muscle, and all the glands, no exceptions. Does that make sense? Any questions? Yes, go ahead. You cannot control it, yeah. You appreciate it. Like if you start salivating, you know that you're salivating, but you cannot do anything about it. You see the difference? And I wanted to say, I wanted to say something incredibly smart about this. Probably wasn't. Makes sense, right? Now, in many cases, students think, oh, motor means like movement. No, not necessarily. When you sit at the table, about to have a dinner, and start making saliva, nothing moves. But that's a motor response. Autonomic motor response. That make sense? Okay. Now, in terms of sensory, what does that mean? Slightly different. Sensations are not conscious or unconscious, right? They just there. So somatic sensations come from the body. What do I mean? Everything comes from the body. I know. Somatic sensations are pressure, temperature, pain. Okay? Now, special sensations. Sight, let's put it like pressure, temperature, pain. We can have position. By position, I mean, look, I bend my elbow. I do not see it, but I know exactly that it is bent because I feel, all the twists and bending my elbow and contraction of muscles and whatnot, okay? So sight, hearing, smell, taste. And visceral sensations are from organs. Again. Any questions? Speak up. When you eat too much and your stomach stretches, you feel it. It can feel like a pain, absolutely. But we kind of separate the sensations that come from internal organs from the sensations, internal organs, from the sensations that come from the skin, joints, and muscles. Does that make sense? Any classification is artificial, and this one is too. Artificial, very artificial. But when we use certain situations, it's easy for me to say, somatic sensation immediately. That's either a pressure on the skin or being burned or something. Okay. That makes sense? Okay. Questions? If not, let's briefly talk about the cells of the nervous system. Kind of outline what they are. So we've got cells of the CNS, central nervous system, cells of the PNS, okay? Cells of the CNS. First and foremost, astrocytes. Okay, what are the functions? Nourishing neurons, providing blood-brain barrier. Okay, now what is blood-brain barrier? Let me show you. So imagine that this is the cross-section of a blood vessel. Those are epithelial cells. Does that make sense? So these epithelial cells right here are attached to each other by so-called tight junctions. You may remember that. So first and foremost, these cells already really tight, nothing can cross these junctions. And on top of that, there are astrocytes that extend their pseudopodia like this. See that? So they prevent virtually any transport in between the cells. Am I clear? So it's a really, really tight barrier that separates blood from the brain. Of course, nutrients and respiratory gases can cross this barrier in a very controlled manner, but things like pathogens or toxins, they have a hard time getting from the blood to the brain. So basically, it protects the brain from any potential dangerous chemicals that may be carried through the blood. Clear? Good? Okay. Microglial cells. Protection. Those are immune cells that can destroy pathogens and debris. Okay? You follow me? Now, those cells are not moving, so they're not very effective. This is why often brain is called an immune privileged cell. You know, it's if infection gets there, you do. Oligodendrocytes. Sorry. They provide electrical insulation. And finally, ependymal cells. They form cerebrospinal fluid. Okay, form cerebrospinal fluid in which our brain is bathing all the time. Now, what about PNS? In PNS, you have satellite cells, nourishing neurons, and you have Schwann cells. Electrical insulation as well. Now, if you're curious, why can't we call Schwann cells and oligodendrocytes just all of them oligodendrocytes? These two types of cells are functionally different. They both do the same, insulate electrically. Schwann cells have an additional function, neuronal repair. So they help neurons to regrow. So far, we're in the same thing. So what do you need to know? If you would look at the PowerPoint, I don't remember if I have like malignancies associated with these cells. You don't need to know. I'm just giving basically what I'm saying is that all those cells can produce tumors, malignant tumors, except for Schwann cell, which produces what's called schwannoma or neuroma. It's a benign tumor. Okay, all others those tumors are rare, and unfortunately, since they are in the brain, they are dead. Okay, because specifically from this astrocytoma, microglioma, they are rare, but outcomes are usually not very good. Okay, we good so far? Now, those are the stage group. Now, what about the main player, the neurons? So what you need to know about a neuron? Please don't laugh, I'm going to draw my classic neuron drawing instead. No, I didn't expect it to be that bad. So that's kind of a neuron, okay? So we've got dendrites, we've got body, we've got axon, we've got here axonal helio, and you've got terminals here. Okay? And in some cases, you may have this, say, Schwann cells or oligodendrocytes. Doesn't matter. And for myelin sheath. So let's break it down. Let's break down what are the functions. Dendrite is a part of a neuron that receives the signal. From where? In the previous neuron. Does that make sense? The signal can be received on the body as well. Then signal, think of it this way. Signals are received on the dendrites. They go through the body to the axon, and they travel down the axon. Am I clear? So for instance, if I would want to illustrate, for instance, we are all neurons. So I transmit signal to Madison, and Madison transmits signal to Brad. Okay? It cannot go backwards. There's one-way transmission. Am I clear? Okay, and I transmit signal from my axon to Madison's dendrites or body, also called soma. Okay? Questions? So basically, like terminals transmit the signal to the next one. Good so far? Now, you see this Schwann cells here? They form this myelin sheath. They wrap the axon. They electrically insulate it. Okay? So why? The nature of a signal that goes through the axon is electrical. It is an electrical signal. It's a wire. Why do you insulate wire? To not lose any electricity. Does that make sense? Insulation allows the signals to travel faster. Okay? Now, what would happen if this insulation will start, will get destroyed? You're going to have a disease called multiple sclerosis. Okay? And your own immune system starts to destroy this myelin sheath. Suddenly, the wires, the axons that used to be really fast, become very, very slow. Does that make sense to you? Signal transmission suffers, and people develop paralysis, paresthesias, develop cognitive impairments, and so on and so forth, depending on which neurons are. Good so far? Okay. Types of neurons. Multipolar, bipolar, unipolar. Multipolar. Multiple dendrites, one axon. You have it illustrated, okay? So multipolar neurons are the most abundant in the brain, and they are very abundant among motor neurons. That makes sense here. So multiple dendrites. This what I pictured is multipolar neuron. Bipolar. A dendrite, a body, an axon. So there's one line that collects. So instead of multiple dendrites, there's one dendrite, one axon. Does that make sense? Good? And unipolar, the body of the neuron is on the side, and dendrite and axon are practically fused. So bipolar and unipolar neurons, very commonly found in sensory transmission, specifically in the sensory nerve and sensory neuron. Good so far? Got it? Okay. Now how do neurons communicate? Neurons communicate through synapses. Synapse can be chemical or electrical. Okay. So what is a synapse? I would say that the best description of a synapse would be it's the place where two cells can exchange some kind of information. Does that make sense here? Just think of it this way. If I will take this marker and throw it together, we're not in the direct physical contact, but we cannot exchange the information. Does that make sense? Generally speaking, of the synapse, this exchange can be one way or both ways. Okay, the signal can become stronger, can become weaker. All kinds of things can happen to the signal. Now, what's the difference between the chemical and electrical synapse? The electrical synapse is formed by the gap junctions between the two cells. So electrical synapse is the flow of charged particles from one cell to another. Now, since these gap junctions are essentially ion channels, and this flow can go both ways. Does that make sense? Do you understand that? So electrical synapses can be formed between, for instance, cardiac muscle cells or smooth muscle cells. And at this point, signal can go either way, doesn't matter. Chemical synapses are formed between what's called cardiac muscle or smooth muscle. Now, chemical synapses are formed between neurons. Okay? And what's important, they are unidirectional. So if we employ my previous example, when we are neurons and I send the signal to medicine, okay, I can send signal to her, but she cannot send signal to me. It's a one-way street. Does that make sense? Now, remember I put here basically the sequence of events in the neurotransmission. I said, receptor, sensory neuron, central nervous system, motor neuron effect. Remember that? Remember I told you that the signal goes in one direction all the time. This is why. Because there are only chemical synapses in the nervous system. And information can move one way. Okay, it cannot go from CNS back to the sensory receptor. Because chemical synapses just they don't work this way. Am I clear? Now, let's talk how chemical synapses work. How, what happens in it. And that's going to be important. So let's draw a terminal. This is called presynaptic terminal. And this membrane right here is going to be a postsynaptic neuron. Okay? So this space right here is called synaptic core or synaptic short. Doesn't matter. I prefer the word. Okay, so what happens? First, there is a signal that arrives at the presynaptic terminal. It is called action potential. It's an electrical impulse. And we're going to talk about the nature of that impulse on Tuesday next week. So far, what you need to know that it's an electrical signal. Okay, so this electrical signal basically changes the charge of the cell membrane, and that change opens the channels, the calcium channels. Now, the concentration of calcium ions is higher on the outside than inside of the cell. And remember the process of movement of ions from their high concentration to their low concentration? Does anyone remember what we call it? The D word. Movement of compounds from high to low concentration. Chemicals to what? They diffusion. Yeah, they diffuse, right? So calcium diffuses into the cell. And it's interesting, so calcium, when it gets into the cell, it works as a stimulus for vesicles that contain a special chemical called acetylcholine. Okay, so that's our. This is our acetylcholine molecules. Okay, these chemicals, acetylcholine, is released. So we call these chemicals neurotransmitters. Okay? Does that make sense? Good? Now look at this. So we have electrical signal. It opens calcium channels. Calcium diffuses into the cell and stimulates these vesicles to release neurotransmitter into the synaptic cleft. Neurotransmitter travels across the synaptic cleft and binds to the channels on the postsynaptic neuron, to the receptors on the postsynaptic neuron. Does that make sense? So this is the receptor. When neurotransmitter binds to the receptor, that generates some kind of a signal in this postsynaptic neuron. Does that make sense? No? Okay. This is neurotransmitter. I'm not going to throw anything, don't worry. This is neurotransmitter. I'm this neuron. Kelly, you are this neuron, okay? Make sense? So what I do, I give you this neurotransmitter. You receive it. And then you can do multiple things. You can stand up and leave the class, okay? Or you can fall asleep. Or you can throw it in the wind. The point is, some kind of a response is generated in the postsynaptic neuron. Does that make sense? This part. Got it? That's it. And I'm going to go over it one more time. So again, action potential, an electrical signal arrives at the presynaptic terminal. What does it do? Tell me. This electrical signal does what? Louder, huh? Opens the channels. Good. So calcium diffuses into the cell. It's like a domino effect. Calcium diffuses into the presynaptic terminal and causes the release of neurotransmitter. Good? The neurotransmitter binds to the receptor on the postsynaptic neuron. So far, make sense? Strictly speaking, this neurotransmitter can do one of two things. It can either excite this neuron, and then the signal will go through, or inhibit this neuron, and then there's no signal. Does it make sense? This time. Good? We're going to talk how this happens. That's going to be later. Don't worry about it. Now it's not important. Now we need to understand conceptually that this neurotransmitter is what generates that signal. Am I clear? Okay. What do we need to do in the end? We need to get rid of that neurotransmitter. Because what's going to happen if that neurotransmitter stays in the synaptic cleft forever? What are we going to have forever? It's a simple question. We're going to have a signal. Does that make sense? Like, there's going to be a perpetual signal. We don't need perpetual signal. We want to control it. Makes sense, right? So like, you make a little signal, a little nudge, and then you shut it down. Because if you need more, you can release more neurotransmitter. You can send another action potential. Okay? So, how do we destroy neurotransmitter? We can destroy it by several ways. So we can destroy it by, it can diffuse away, which is not good. It can be destroyed by enzymes, so enzymatic degradation. Or it can be taken back. So this neurotransmitter can be taken back into the presynaptic terminal. Now, let me, in a fairly slow manner, put all the pieces of the puzzle together. Remember, the signal that goes to the neuron is an electrical signal. So this electrical signal arrives at the presynaptic terminal. If you are silent, I assume that it's clear. If it's not clear, say, I don't get it, or just do this. There's not a lot of neurology, okay? Runs, and it opens calcium channels. Since calcium concentration outside of the cell is higher than inside, calcium diffuses into the cell. Calcium causes the cell, this terminal, to release neurotransmitter to the synaptic cord. The neurotransmitter binds to the receptor on the postsynaptic neuron and generates some kind of a signal. And then neurotransmitter is removed from the cleft either by reuptake, you can take it back, enzymatic degradation, basically destroyed, or it just passively diffuses away. Does that make sense? Now, sorry I hold you a couple minutes. I'll give an example, 2 examples. Why I pay so much attention to this? There are phosphoorganic compounds that can inhibit enzymatic degradation of acetylcholine. Example is a gas called VX. You may have heard of it. It's the chemical weapon And look what happens. If somebody is exposed to VX, instead of being destroyed, acetylcholine stays in the synaptic cleft and perpetuates the signal. The signal keeps going and going and going. And people develop like massive responses. They can develop paralysis, spastic paralysis of the diaphragm. They will be salivating. They will be urinating. They will have diarrhea, abdominal cramps, all of it at the same time. So it is not free because the enzyme cannot destroy neurotransmitter. Okay. Another example, really good example, is I don't remember which exact drug. Yeah, it's Prozac. Yeah. So Prozac inhibits the neurotransmitter called norepinephrine from being brought back into the presynaptic neuron. Does that make sense? So now you have a ton of norepinephrine staying in the synaptic cleft, keeps signaling. Norepinephrine is the feel-good neurotransmitter. Prozac is anti-anxiety medication. It makes you feel good. Does that make sense? So remember, if you inhibit the destruction, you create a permanent signal. Good? Let's wrap it up and we'll talk about neurotransmitters next time.